Welcome to our next set of college algebra notes. We're on Unit 2, Outcome 6. In this section, we're going to talk about polynomials, some techniques for graphing polynomials and kind of understanding their shape just by some of the aspects of the equation of a polynomial. Before we get too much into all that, let's just remind ourselves what a polynomial is. You should have seen these before, but we've worked with them already this semester. But a polynomial function is any function that looks like this, where it's going to have terms where there's going to be the a sub n's here are going to be like real numbers. The exponents, the powers, are going to be whole numbers. So x is going to have whole number powers, things like 1, 2, 3. There's no negative or fraction powers, and there's going to be real numbers in front of the x's. These are the polynomials. We call the very first term right here, this a sub n, x to the n, a leading term. So it's just the one with the highest power. So a sub n is going to be the leading coefficient. Remember, the coefficients are the numbers in front of your x. And the degree, remember, degree is the power. So the degree of this function is n. So the degree is the highest power of the polynomial. So that's what a polynomial is. This is again the generic forms. The real, forms we're used to are like, those 2x squared plus 3x plus 5 kind of things we're used to seeing. Those are polynomials. Usually we refer to the polynomial by the degree. If they just have a single x to the first, just a plain x, we call them linear. They make the nice straight lines we're used to dealing with. So think of like the y equals mx plus b type equations. We call them quadratics if they have degree 2. So quadratic, of course, is going to be our parabolas that we've been dealing with. They have an x squared. We'll call them cubic if they have x to the third. So cubic, we've seen a few of those already. And then quartic, which is degree 4. And then beyond that, we don't keep using special terms. Anything above 4, we kind of typically just refer to by the degree. So it's the 5th degree or 6th degree or 7th degree. So we'll just look at the highest power and kind of use that. So most of the time, there's not a lot of reason to work beyond the first 4. So that's why the other ones are a little more rare. And so we'll just use the degree. Okay, so first off, you can actually tell information about a polynomial without graphing the whole thing just by looking at the leading term. So there's this interesting thing. The behavior of polynomial at the ends, so when x is going really big or x is getting really small, so as you're going off to infinity in the right or negative infinity to the left, is called the end behavior. And you can actually look at the degree of the polynomial, the leading term, and you can actually learn things about the end behavior. So we're going to figure that out, puzzle it out from this chart I have down here. So first off, we're going to look at these ones. Notice that these ones all have even degree. This one's got degree 2, this one's got degree 4, this one's got degree 6, and this one has degree 10. Now notice they didn't put it at the beginning. It's not the first one, it's the one with the highest power, right? So these are all the highest powers on those. These all have even degree. And noticing the top ones versus the bottom all have odd degree, right? So you can see here these are degree 3, degree 5, degree 7, and degree 9. Well, the big difference is the even degree versus the odd degree, the ends of the even ones always match, right? Versus the odd, you can see on the odd ones, the ends are always going different directions. So an even degree, if you have an even degree polynomial, the ends match. That's always going to happen. If x to the 8th, x to the 10th, x to 200, no matter what it is, if it's an even number, if the ends are going to go the same direction, whether they both go up or both go down, they're going to go the same direction. Odd degree, they're always going to go different directions. They're not going to go the same. So, different directions. Ends. So if one goes down, the other one goes up. If one goes up, the other one goes down. That's always going to happen if they're odd. So odds are always going to be different. Evens are always going to be the same. Now beyond that, you might have noticed that some of these top ones go up and some go down. And there is actually a reason for that you can actually pay attention to. You notice that the ones that go down before the x, the ones that go down actually have a negative coefficient. The ones that go up, and the ones that go up are going to have a positive coefficient. So you can see here, I just have 1/2 is positive. There's no number there, but we know by default that means there's a 1 there by default. So if a sub n, which is the leading coefficient, if it's positive, bigger than 0, they go up. both of those ends go up. But if a sub n, the leading coefficient, is less than 0, so it's negative, it goes down. So just by looking at the polynomial without even graphing it, without doing any math, really like solving, plugging things in, we can just kind of look at that leading term. You can get a basic idea of what the shape should look like. Really informative. So you just look at the first one and say, okay, if it's degree even, I know they're both going the same direction. Positive, it goes up, negative, it goes down. And we kind of saw that with our polynomials, right? With the polynomials, we saw x squared, the polynomials, the parabolas. With the parabolas, the x squared parabolas, they're always x squared, so they always had both ends go the same direction. And we saw that if there was a positive at the beginning of the parabola, it would always go up. And if there was a negative, it would always go down. So that behavior actually was already showing up with the parabolas. Okay, odd degrees, same thing. You can tell by looking at the sign. If it's got a negative in front, so if it's got a negative in front, you'll notice that it goes down to the right. And if it has a positive in front, here this has a 1/2, and it has a positive, this one doesn't have anything, which we know means a 1. If it's got a positive, it goes up to the right. So if a sub n is less than 0, if it's negative, it goes down to the right. And if a sub n is positive, if it's got a positive number in front, so it's bigger than 0, it goes up to the right. It's going to look like this versus a negative, which would look like this. And up here, I guess I could have drawn that. I could show this one's going to go up, both ends, and this one's going to go down, both ends. So there you go. So a lot of information you can get just by looking at what happens with the leading term, the leading coefficient. The rest of this stuff still affects the polynomial and its shape and all that, but if you just want to know what happens at the ends, you can look at just that leading term. Okay, another thing we need to know when we're kind of looking at the polynomials in their graphs is to notice the zeros of polynomials. So a zero polynomial, remember we mentioned this earlier because we mentioned it with functions. A 0 is a number that you plug in and the result, or the y value, is 0. So for this polynomial right here, we have x squared minus 2x minus 8. You can see that if you plug in a -2, you get out 0. There's a point right there at -2, 0. So -2, if I plug that in for all the x's, would give me 0. So -2 is a 0. So this is going to be a 0. And then 4 is also a 0. If you plug in 4 for all the x's, and you get out 0. So -2 and 4 are zeros. So the zeros for this polynomial are -2 and 4. But zeros, you'll notice, are the same thing as being x-intercepts. Because if you're 0 height, that means you're right on the x-axis. So polynomials, their real zeros are going to be x-intercepts. Now, why does it say real, not just all zeros? Imaginary zeros won't show up on the graph, so they won't be x-intercepts. So a polynomial can have imaginary or zeros with negative roots in them, and those don't show up on a graph, so they won't be x-intercepts. But every real zero will show up on the graph and be an x-intercept. We'll talk more about the imaginary zeros of polynomial functions later on. We'll get to that later. But for now, it's important to note that if you have a real zero, nice real number that solves your polynomial because it makes it equal 0, it'll be an x-intercept. So same thing over here. We can see that -3, -1, and 2, these points right here, those are zeros. So those are your zeros. And that means that they are also x-intercepts. So -3, -1, and 2. And so you can see, with the parabolas, we always got, we typically got 2 real zeros. With higher power, like this one's degree 3, you can get more. So you can actually get more and more real zeros if you have a higher degree polynomial. Okay, so when we're solving quadratics, we figured out that we could use that zero product property where it's 0 if and only if one of the things you're multiplying is 0. We can apply this even for larger polynomials. So if you have something, this one actually I think would be degree 4. That's what this one is degree 4. This one's already factored for us, thankfully. We're not going to try and factor these ourselves yet. We'll do that later, though. This one's all factored for us, and so we can see since it's all multiplied, if we want to find the zeros, that means just set it equal to 0, Well, if it's all factor, we're trying to set it equal 0, then we can solve it by setting each part equal to 0. So we just set each factor, or each part, equals 0. So we get the first part is x, so we get x equals 0. Second part is x minus 2, so we get x minus 2 equals 0. X plus 3 is the next part, so we'll set that equals 0. And 2x plus 1. So we set that equals 0. So because it's factor, we can just take all these pieces, set them all equal 0, and that will find all the zeros for us. The first one's done, right? X is 0, that is a 0. If you put 0 in here and multiply, everything's 0. Here we just add 2 across. So we see that x equals 2 would be the next 0. So I plug a 2 into here. 2 minus 2 would be 0. And so if this part's 0, the whole thing's 0. Subtract 3 across in the next one. So we see that x equals negative 3 is a 0. So plug negative 3 in there. This 0 makes everything 0. Last one here, I have to do a couple steps. First, subtract 1 across. So you get 2x equals negative 1. Divide by 2 on both sides. Get rid of that 2. We get x equals negative 1/2. And if you put a negative 1/2 in here, half of 2 is 1, and if this is a negative 1 plus 1, you would get 0. So all of these guys are all zeros. So all 4 of those numbers are zeros. If you graph this polynomial, those would all be x-intercepts. Because zeros that are real, like this, are x-intercepts as well. So if I was trying to graph this, these would be the 4 places where it crosses the x-axis. So if you have a factor, you can see finding zeros is not that hard, because you just have to set each part equal to 0 and solve all those parts. And again, they can get more than just 2 zeros, because as you get bigger and bigger polynomials, you're going to have more opportunities for zeros. Now, some zeros are repeated. They might have the same 0 more than once. That was possible with the parabolas. I said that you could have a repeated real 0, where you have the same real 0 twice. So you can have polynomials where you have repeated zeros. We refer to the number of times that it's a 0 as the multiplicity. So the multiplicity is the number of times a 0 solves your polynomial. So for example, down here, I have x plus 9, which if I take that and set that equal to 0, x plus 9 equals 0, and subtract 9 across, we can see that x equals negative 9 is a 0. But notice that this x plus 9 is actually x plus 9 cubed. So it's like having x plus 9 times x plus 9 times x plus 9, right? 3 times. Since it's in there 3 times, every one of these is going to be solved if you make x a negative 9. So that one's going to be solved because that'll be 0. This one will be 0. This one will be 0. They'll all be 0 if you plug in x equals negative 9. So this negative 9 is a 0 3 times. So negative 9 has multiplicity of 3 because it's got a degree 3. So the degree really tells you the multiplicity. You can see that that one's degree 3, so it has multiplicity 3. X minus 1, again, this one happens 4 times. And again, this one would be 0 when x is 1. So we have a 1. So 1 has multiplicity. Multiplicity, spell that right, multiplicity 4, because it has degree 4. So 1 actually is a solution 4 different times, because we have 4 of these x minus 1s in there. Lastly, we have this x minus 15, which of course if you set that equals 0, you get x equals 15 when you add it across. This one, since there's no degree here, well, we know the default degree is 1. This one just has multiplicity 1, so 15 has multiplicity 1. So if there's no higher power, if it's just that parentheses without any power, that's always default 1, then it's going to be multiplicity 1. And that's going to be your most common multiplicity. Most things will have multiplicity 1. But anytime you have a higher degree like that, when you have the same parentheses repeated, then it's going to have a higher multiplicity. Now, multiplicity, why do we even care? Well, we care because it actually affects the way the graph is drawn. So the graph will look different depending on the multiplicity. So there's 2 main things. First, you can have odd multiplicity. So if your power, your degree, is odd, so you get odd multiplicity, then the graph is going to cross the x-axis at that 0. So remember we said that every real 0 is an x-intercept. And so if you have an odd multiplicity 0, so the multiplicity is an odd, then it's going to cross. So like here, this one right here has odd power on the negative 2 multiplicity, or the negative 2, 0. So this one actually 2 would be the 0. 2 minus 2 is 0. So 2 is a 0, has odd multiplicity. That's why at 2, it's crossing. Over here, this one has odd multiplicity. X plus 1 has odd multiplicity. So it crosses at negative 1, which is a 0 for that. So these ones are odd. Conversely, if you have an even, so if you have a power that's even, so the degree is even, then you're going to be tangent. Tangent means you bounce off. You know, you're not gonna cross through it. You're gonna be tangent to it, so you're gonna bounce off at that 0. So like these ones here, this is even, right? This is even, and so they bounce off. You can see they don't actually go through; they bounce off. So tangent, you can think of as bouncing. It bounces. So if you know that about a graph, you actually know the behavior. You know it's not going to bounce off. If it's odd, it's going to cross through. But if it's even, it's going to bounce off and keep on the same side, which can be helpful when you're trying to look at the graph or understand the graph, see what's happening. So we're going to figure out where this function would cross the x-axis based on the multiplicity. So first off, this first one, right, we have multiplicity 4. So x equals 8 is a 0, right? 8 minus 8 would be 0. And it has multiplicity 4. Since it's got an even multiplicity, that is even, well, we said that even numbers bounce off, right? If it's even, it bounces off. So this is going to be tangent, or bounce. Next one, x plus 2 has a 6. Well, that's still even, right? So here, x equals negative 2 would be the 0. Negative 2 plus 2 would be 0. And that has a multiplicity of 6, but that's still even, right? It's still an even number. It's just a different even number. As long as the power is even, the degree is even, you have even multiplicity, then it's going to be tangent. So it's also going to be tangent there. Last one, x minus 7 has degree 3. So this one, x equals 7 would be, so 7 minus 7 would be 0. And it has multiplicity 3, which is odd. Since it has odd multiplicity, it's going to cross here. So now if you're trying to graph this, by hand, or if you want to draw it out, you know that you would be tangent at 8 and negative 2. So on your x-axis, you bounce off of 8, you bounce off of negative 2, but at 7, the line would cross over it, it would cross through it. So it'd go from one side to the other. So that's important stuff to know when you're trying to draw the graph and understand what the graph looks like. So just by looking at the multiplicity, you can know those facts. Okay, a couple of little side things. So when you're working with polynomials like this, it's important to be able to check if something's a 0. So here they just want to determine if 2 is a 0. If you're trying to figure out if something's 0, all you have to do is just plug it in. So they say use substitution, that just means plug it in. So if 2 is a 0, that means that if I do f of 2, the polynomial should give me 0. So I'm going to try plugging it in and see if it gets me 0. So I just get 2 cubed, because 2 goes in for the first, x minus 4 times 2 squared, so I get 2 squared, minus 11 times 2. I put parentheses because I want to remember that this is multiplication, right? When I put that 2 in there. 11x means 11 times x, 4x means 4 times x, and then plus 30. Of course, you always do powers first before you multiply. So 2 cubed is 8, right? 2 times 2 times 2. 2 squared is 4, so this becomes minus 4 times 4. Always powers before you multiply. 11 times 2 is 22. Here, 4 times 4 is 16, so I get 8 minus 16 minus 22 and plus 30. So we do 8 minus 16, that's a negative 8. Minus 22 makes a negative 30. Plus 30 gives me 0. So it does check out. This is a 0. So a 0, remember, means that if you plug it in, you get 0 out. So the point 2, 0 is an x-intercept, and 2 is a 0. Because it's a real 0, it gives us an x-intercept. So if I was drawing the graph of this function, I know that go 2 to the right, and then right there it would have a 0. I don't know the multiplicity because I didn't check that. I just know that 2 is a 0. So I don't know if it crosses or is tangent, but I do know that there is a 0 at 2. Okay, another thing. When given a polynomial, it's not always super easy to find the leading term or figure out the degree. So you might get a polynomial written something like this. This one, because it's already factored, you can't just look at this and say right off the bat, like, This is the degree. You have to do a little bit of work first. So the trick here, instead of having to take this and sit here and multiply x squared plus 1 3 times, FOIL that out a whole bunch of times, and x to the 5th minus 1, FOIL that out a bunch of times. You could do that, but it'd be really long and time consuming, and easy to make mistakes. So instead of doing that, since all we care about is the leading term, right? We're just trying to find a leading term, that's all we're trying to do. We're not trying to get the whole polynomial. There's a trick. What you can do is you can ignore everything that's not going to be part of your leading term. The leading term is only going to include the big parts, like the x squared, x to the 5th. It's not going to include like a 1, because this 1 has lower degree than the x squared. We're only looking for these like leading stuff. When I FOIL this out, if I was FOILing, I do first, and that would give me the highest degree. Everything else, like the outside, the inside, the last, it's going to be lower degrees, and so they're not going to be part of the leading term. So I can actually just ignore this stuff, the stuff that's not going to be part of the leading term. So instead of trying to do this whole problem, I'm just going to look at the x squared that's being cubed and the x to the 5th that's being raised to the 4th power. So I'm going to just do that instead of trying to do all the parts. I'm going to ignore these extra terms because they're not going to be part of a leading term. I want to look at the leading term. Here, remember that when you have a power to a power, you multiply the powers. So x squared to the 3rd becomes x to the 6th. X to the 5th to the 4th. 5 times 4 gives us x to the 20. So a power to a power, you multiply the powers. And remember that when you're multiplying two things with powers like this, you add them up. I have 6 x's here, I have 20 x's here. Total, I have 26 x's. So the degree of this one, the degree is 26. And since these are just both had 1s in front, when you multiply, you just get a 1 in front here. So there's just a 1 in front there. You can write it, or you can just leave this x to the 26. But now we know that. We know what the leading term is. It's 1x to the 26, and the degree is 26. So you can ignore these smaller parts and figure out the leading term, the leading degree. Let's try one more. So again, we're going to ignore small stuff. So like, I've got negative 2x to the 5th. I don't need the minus 4 because the 2x to the 5th has a way higher degree. So that's going to be the important part. X squared beats out the plus 7, so I'm going to ignore the plus 7. So I'm only going to look at the parts with the higher degrees because they're going to be part of my leading term. So I'm just going to take this negative 2x to the 5th, to the 3rd power. I'm going to take this x squared to the 4th power. And don't forget the x in the front, because that does have the highest degree of the stuff that's outside. Inside the parentheses, this was the highest degree, but outside, that's the highest degree. Okay, so here again, I would take this and do the 3rd power. When you have a number as well, remember that you take this power and you do distribute it. You can distribute powers to multiplication. You can't do that with addition or subtraction, which I saw some people doing on the test, so you gotta be careful about that. But you can do it here. You can always do degree distributed if it's multiplication. So I do negative 2 to the 3rd. Well, 2 times 2 is 4, times 2 is 8, so that becomes 8. And 3 negatives make a negative, because 2 of them cancel, there's 1 left over. X to the 5th to the 3rd, we multiply the powers, so we get x to the 15th. Don't forget the x in front. Over here I have x to the 2nd to the 4th. So again, I multiply those powers and I get x to the 8th. Let's multiply that a little bit more. You get x times negative 8x to the 15th. Well, we just multiply the x's, so we add the powers. We always know there's a default 1 there, so we get x to the 16th times with negative 8. And then last, we have this x to the 8th, x to the 16th, so we add those powers, right? When we multiply the x's, we add the powers. So we get 24, so we get negative 8, x to the 24. So again, the degree is 24, because that's the power, and this is our leading term. So that's what we're looking for, the leading term and the degree. I forgot to box those ones. So leading term and the degree. And again, you could do this really easily if you just ignore the smaller terms, the terms with less degree. They're not going to be part of the leading coefficient. If I wanted the whole polynomial, if I wanted to look what the whole thing looks like, expand it out, then I would have to take those and I have to multiply a whole bunch. But thankfully, all I really want to know is what the leading term looks like. Then I can do things like tell you, because it's an even degree, both are going to go in the same direction. Because it's a negative coefficient, these are both going to go down. So remember, we can talk about stuff like the end behavior. And so the end behavior on this one is that it's going to look like this. Because the negative 8 is less than 0, so it goes down, and 24 is even, so they both go the same. Versus up here we had 26 is even, so they go the same direction, but the one in front is bigger than 0, it's positive, So this one's going to look like this because they're both even. You know, that's what the end behavior is going to be. So it's pretty powerful, even without having the leading coefficient to start with. If you just find the leading coefficient for yourself, then you can see what's going to happen. So without even graphing this fully, I can tell you, oh, it's going to have this basic shape or that basic shape. You might do some wiggling in the middle, but at the ends, I can tell you what's going to happen. Okay. Now, we talked about the end behavior, and we talked a little bit about the zeros, but there's actually a really cool fact about the number of zeros that we're going to introduce at this point. So when you're working with these polynomial functions, you can use the leading term test, figure out the end behavior, but there's one more fact, the fact that there is a limit to the number of zeros. So a polynomial function with degree n, so if n, the power is n, then it can have at most, no more than, at most, n real zeros. So that's the maximum number of zeros. So that's why with the parabolas, the x squared, the quadratic functions, they said x to the second, right? They never had more than 2 zeros. They could have less, but they can never have more. That's why when you get higher degrees, like degree 3 or degree 4, you end up with more zeros because they can have a higher maximum number of real zeros. So a degree 5 polynomial, x to the 5th, it could have 5 zeros. It can't have more than 5 zeros. The most it can have is 5. That's its maximum. Since the real zeros are also x-intercepts, that's also the maximum number of x-intercepts. I don't know why, but your book and the homework will ask for both numbers like they're different, which is really funny and kind of ridiculous. Like it's going to ask you, what are the number of real zeros, the maximum number? And you'll say it's 5 for degree 5. And they'll ask, what are the number of x-intercepts? And you'll say, still 5. Because every real zero is an x-intercept. So I don't know why they do that. I think it's really silly to break those apart because we just talked about how real zeros are x-intercepts, but they'll ask you for both numbers like they're different or something, but they're not. Next thing, when you draw it, it could turn, right? We saw those parabolas, they make one turn. The number of turns it can make is also limited. So the most turns it can make is always going to be one less than the degree. So the number of turns it can make at most one less turns. These are going to be like your relative maxima. So like when you draw your parabola, x to the second, the most it could have is 2 zeros, and the most turns it can have is 1, which is why it always looked like this or like this, right? It only could have one turn. Because if we take that degree 2 and subtract 1, we get one turn. But now if you get to a degree 3 or degree 4, you can have more turns. So you can actually have more wiggles and stuff in the middle. So that can happen. It doesn't always happen. Sometimes they don't have more wiggles. And sometimes they only turn once, but it's possible for them to do that. Okay, so let's figure this out for a couple of functions. So here we go. First off, we see that this one has degree 5, right? So it's degree 5. So how many zeros can it have? Well, it can have up to 5 real zeros. Can't have more, right? Can't have 6, 7, 8. You can have less. It could have less real zeros because it's always possible that some of the zeros are imaginary. We saw that we solved parabolas. Sometimes they had less than 2 real zeros because they had imaginary zeros or real complex zeros. So degree 5, it can have up to 5 real zeros. It can have less, but it can't have more. And then it can have up to 5 x-intercepts. Like I said, it's going to ask for both of these. It's really silly because these are always the same. They have to be the same. Every real zero is an x-intercept, so those are always the same. So I don't know why they ask for them separately. It's kind of silly. But the turning points is different, right? So it can have up to 4 turning points. It can't have more. It can have up to 4 turning points. So for example, like this one's a -1, so we know it's going to go down to the right. So it's going to start with the number up here, a line, an end behavior going up here. It's going to come down. It might turn once, turn twice, turn 3 times, turn 4 times. But now it can't turn anymore because there's 1, 2, 3, 4 turns. So from there on out, it has to go down. And so that would be an option. It could do less, right? It can do less turns, but it can't do any more turns than that. That's the most turns. That's what that would look like. Because it has up to 4, degree 5 can do at most this. It can't do any more wiggles than that, though. The next one's degree 6, right? So this one's degree 6. So the real zeros are going to be less than or equal to 6, right? There's no more than 6 of them. The x-intercepts, again, silly, but it's the same thing, no more than 6. And the terms, well, the number of turns here could be less than or equal to 5, right? That's always less. This one, because it's positive and it's an even power, we know they're both going to go up. So it would start like this, where it's coming from the up direction on the one end, and it'll come down and eventually it'll turn once, twice, 3 times, 4 times, 5 times, and it looks like that. There's 1, 2, 3, 4, 5 turns. And that's the max, right? You could have less turns, so it could wiggle less, but it can't wiggle any more than that. That's the most number of turns it can have. So it's nice to know this, because then you can kind of see what the basic shape could look like or should look like. Again, you could have less wiggles, so we can't always guarantee all those wiggles are there. You know, you can take out some of the wiggles and that's still be a degree 6. But that's the most it can wiggle. That's the most it can have this up and down, these relative maxes and mins. Okay, the last part of this section, we're going to actually take all that information we've just put together, things about the leading terms, the number of zeros, all that stuff, the number of wiggles, and we're going to graph a function without using a calculator. We're just going to do it by hand. And we'll see, we're not going to get a perfect graph, because if we want a perfect graph, we'll use technology, right? We'll use a calculator, but we'll get a basic idea of what the graph looks like, so we can look at that without even having to pull our calculator out. Okay, so first off, leading term test, because the leading term test figures out the end behavior, right? So we know what happens at the ends. So before we can do anything else, we need to figure out the leading term. But this was one of those where they don't give it to me that way, right? They don't give me x to the whatever power at the beginning. So to do that, to do my leading term test, I'm going to take the high x parts, right? So I have an x part here and an x part there that's being squared, and an x part there. I'm just going to multiply those together. I'm going to ignore the numbers. Or I should actually include the 1/8, because that's going to tell me whether it's positive or negative. So, but the plus 4, I'm going to ignore the -3, the plus 1, because they're all extra numbers. I'm just going to multiply these parts together. And that one is just x squared, right? Because x to the second, x squared. So you x times x squared times x, well, that's x to the first and x first. You add them up, and you get x to the fourth. And then there's the 1/8 up front. So by the leading term test, it's even. The degree equals 4 is even. And because it's positive and even, 1/8 is bigger than 0. Because it's even and positive, we know that it's going to look like this. If it has even degree and a positive number, they're both going up. So the ends look like that. So then I'm going to have an arrow going up this way at the end and going up this way at the end. I don't know, exactly where they fit, but I know when I'm done, they should look like that. If I have anything going down, I'm not doing it right. They should both go up. So that's the leading term test. Next thing, look at the zeros. Find the zeros. Remember that all real zeros are x-intercepts. Same thing, real zeros and x-intercept. So here I notice that each one of these parentheses is going to give me a 0. So x plus 4 is going to be one of my zeros. So that means that x equals -4 is 0. X minus 3 is a 0. So that means x equals 3, because I have to add 3 across. And x plus 1 is a 0. So subtract 1 across, so I get x equals -1. So I got 3 zeros. 1 at -4, so go 1, 2, 3, 4. There's one of my zeros. 1 at 3, so 1, 2, 3. There's another 0. And 1 at -1. So those are my 3 zeros. Now, the next thing on this one, it's going to say, hey, go ahead and once you found the zeros, figure out the sign between each one. And you can do this, but I like to do it a little differently. So what I'm actually going to do is I'm going to take this 6th step, because this is what your book says. I'm kind of changing from the book. I'm saying, let's do number 6 next. So instead of a check method, I like to use number 6 at this point to figure out what's going to happen here with these. So it says, just use multiplicity at the end to check things out. I'm going to use multiplicity right now. Remember, multiplicity, the power on your different zeros, tells you whether it crosses or bounces. So I can look at things like this. X plus 4 has degree 1, and that's multiplicity 1, which is odd. We said if it's odd, it crosses. So we know that at this point it's going to cross. If we look at the next one, this x minus 3, that has degree 2, right? So this is multiplicity 2, which is even. So this one bounces, it's tangent. It's not going to cross through, it's going to bounce off. Last one here, x plus 1 is also degree 1, so it's also 1 here. And so it's odd, multiplicity. 1 is odd, so this one crosses. So I know for the first one, this negative 4, it's going to cross through. For the second one here, this is going to cross through because it's the negative 1. And this last one, the 3, it's going to bounce off. Now I don't know, I shouldn't say this yet. I was going to say I don't know which direction top to bottom, but the nice thing is because of the end behavior, I know to start with I have to be coming from this direction, right? I'm going to be coming from this direction. So when I get to this point and I cross, it's going to go this way to cross through. Then I get to this next one, the negative 1. So when I have to come back to hit it, when I hit it, I'm going to cross through again, right? So I'm going to go through. I get to this last one and I am tangent, so I bounce off. So actually that is pretty much all I need, right? So I can actually mostly kind of draw the graph from that. If you want a better graph, it's good to do number 4, which number 4, we want you to find the 0, or the y-intercept. So let's go ahead and just do that. Number 4, we'll actually find the y-intercept. So y-intercept you can find just by plugging 0 in. It's an easy thing to plug in, so that's why we'll do it. So if we plug in 0, so if we do f of 0, so we get 1/8, 0 plus 4, 0 minus 3 squared, and 0 plus 1. Well, we just got to multiply it out and we'll get the 0. So it's 1/8 times 4, 0, that's times negative 3 squared, which is 9, and then 1. So 1/8 times 4 is 4/8, which is 1/2, and then times 9 equals 9/2. And of course, multiplying by 1 doesn't really change anything. So we can see that the 0 here is 9/2, or 4.5, right? So 1, 2, 3, 4.5. That's going to be that 0. That's your y-intercept. And it's just a nice thing to know. We see it's pretty easy to find. So by using the y-intercept and our crossing, we pretty much can graph this. Now it's going to say you might need more function values, and you might need more values depending on the situation. This one, we found all 4 zeros. We found 4 different zeros. This is degree 4, so we have 4 zeros. Some polynomials, like I said, will have less than the max, but this one has the max. And it looks like this. So it's going to kind of come down through here. It's going to hit all the way up there, bounce off this one, go this way. Now again, this is not perfect, right? I didn't get any other extra values. So if I needed something more precise, I either like plug in more numbers, like I say, what happens at 6, 7, 8, to find out where this looks like, or at -6, -7, and that would give me more precise values. But if I want it really precise, I'm just going to pull out a calculator and graph it. In fact, I could just graph something like this in a calculator. If you really don't want to have a messy graph, if you really want to have a nice perfect graph, just go to your y equals and type it in as it is. I'm going to just type 1 divided by 8 times the parentheses x plus 4, parentheses, times parentheses x minus 3, times, oh, don't forget to square that one, and then times parentheses x plus 1. And then I graph it. Oops, my dimensions are messed up. Window, okay, zoom, we're going to do zoom 6. I was using this for stats class last time. Oh. Oh, yeah, I left it on for, okay. Sometimes you'll get that invalid dimension if you use it for stats class and then forget to turn off your stats graph. That's what happened. I forgot to turn off my stats graph. Okay, so there, that's kind of what it looks like, right? It comes down from the top, it goes down below, comes up, it bounces off, and it goes back up. Again, mine looks weird because I made it wider than it should have been and all that because I didn't check points out here. So if you want it to look more nice, you just say what happens if I plug in, 6, 7, or -6, -7, and you can get a better graph. But if you want to look at the real graph, of course you can always graph like this. If you trace, you can always look and see what you have. Like, what was 6? Well, 6 is 78, and it's way up there. Way too high. 5 is 27. 4 is 5. There you go. So I could see, okay, if I go 1, 2, 3, 4, this one's supposed to be at 5. And so you can see, oh, that's supposed to be like way up here. So it actually should be going up faster. That's why mine looks funny. But But we're just trying to use what we have without a calculator. We're saying, okay, if I look at the leading term, if I find the zeros, and if I think about the multiplicity, because again, that's what we did, we used the multiplicity, we can get the turning points, and that'll give us the real version of the graph. Now, they do mention here, they're in option number 3, is to find what the sign is. So what you can do is you can actually go through and you can say, well, what happens between values? If I'm doing sign, if I'm saying, okay, is it going to be down here or up here? You can pick a number that's between your two intercepts, your x-intercepts, like -1, 2, so like -2, and you can like plug in -2 and see what's going to happen. Are you going to get a positive or negative? So put -2 in here. This one becomes -2 plus 4 is a +2. That's positive. -2 minus 3, that's going to be a negative, but it's squared, so it's going to be positive. And then -2 plus 1, this is going to be a negative, because -2 plus 1 is -1. So negative times positives gives you a negative, so this one's going to be negative. I don't even have to figure out what the number is. I just have to know it's going to be negative. And you can see that, yes, it's going to be down here. And so it is negative, like they said. So you could do that. So if you really wanted to like use the signs instead of using the crossing, you can figure out where stuff is just using the, whether it's negative or positive at that point. And that's what they're talking about with this one, is you'll determine the sign at of the section, the part in between. So it's a different way to do it. I think I like the multiplicity a little bit better. I think it goes a little bit faster than having to sit there and figure out the signs for different parts. So that's what I usually use. Okay, let's graph one more and then we'll be done. So same thing here. We're going to use the same process. First off, let's figure out just what the leading term is. So we'll do the leading term test first, because if we can figure out what's going on with the leading term, then we can kind of figure out what this is going to look like. So again, I'm going to look at the stuff that's being multiplied. I'm going to ignore like the -4 plus 2 minus 8. I'm looking at just the terms. So we have the x squared, that over 12 is going to be part of the leading term. I have an x from this one, an x from that one, and an x from that one. And that's it. These are all just x's, right? So this is going to be my leading term. So I multiply, well, x squared times x times x times x, that's 5 x's, right? So it's x to the 5th. And this 12 is actually our leading coefficient. You could think of it as like a 1/12, right? If you take a fraction 1/12 times x to the 5th, the x to the 5th would go to the top. So that's what this is like having a 1/12 in front. So by looking at this, we can see that the degree is odd, and then the 1/12, the coefficient is bigger than 0. So it's positive and odd. Remember, positive and odd means it's going to look like this. So on the left side, it's going to be coming from the bottom. On the right side, it's going to be going up. So it's going to have this basic shape. It's going to do some wiggling in the middle, but that's the basic shape. These are the ends, right? So we know it's going to start from this end, go up as it goes to the right, with some wiggling going on in the middle. Okay, that's the first thing. Next thing we need to figure out is the zeros. So let's figure out the zeros. And again, we'll just look at each parentheses here is going to be 0, and including this x squared is 0. So if you have x squared equals 0, that means that x equals 0 is a 0, right? That's one of your zeros. The x minus 4 equals 0 is going to give us that one of the zeros is 4. The x plus 2 equals 0 is going to give us a 0 at -2. And the x minus 8 is going to give us a 0 at 8. So those are going to be our 4 zeros. We're going to have 1 at 0, so there's a 0 right here. 1 at 4, so 1, 2, 3, 4. There's going to be 1 right there. 1 at -2, so it's going to be back here. And 1 at 8, right? So 4, 5, 6, 7, 8. So 4, 8, 0, and -2. And those would be our 4 zeros. And like we did last time, let's use the multiplicity, right? So the multiplicity will tell us how many times it crosses, or if it goes through. And the only one that's actually even is this one. This one has multiplicity 2, and it's even. So this one's the only one that bounces. So at 0, it's going to bounce. Now if I look at this, what's going on? I see I'm going to start from this way. I'm going to hit -2. And at -2, this is odd. So this is multiplicity 1. All these ones are multiplicity 1, right? Multiplicity 1 is odd. So it's going to come up to here. It's going to cross through. And then it's going to hit the 0. And since it's coming from the top, it's going to bounce like this. So it looks like that. Then I go to the 4, which is also multiplicity 1. So odd. So when it comes to the 4, it's going to go through. And then the last one, this x equals 8, this one's also multiplicity 1, which is odd. So when it comes up from the 4 and hits that 8, it's also going to go through. So there you go. So without doing a whole lot of work, of actually, solving things, I know that the basic shape this is going to have is it's going to come from the bottom left. It's going to go up through this point, come back down, hit this point, go back up, come back down, and then come back up, and eventually it's going to go that way. And again, this isn't perfect, right? If I want a nicer graph, I use a calculator, but this gives me the basic shape. I can see that it's going to have 1, 2, 3, 4 turning points. It's got 4 zeros. All that information, it's pretty handy to have. I have that all. One thing, I didn't find the y-intercept, but I didn't need to, because remember that as soon as I found out that that was a 0 right there, I also know that's the y-intercept. So that's why I didn't bother plugging in 0, because I could see right there that was the y-intercept. So in the last one we found the y-intercept because it was different, but this one the 0 was the y-intercept. So that's the graph, and it's just a quick and dirty graph. It's not perfect. If I want a really nice version of this graph, I just type this on my calculator and get a nice version of the graph. But if I want to be able to just look at it real quick, if you want to be able to look at a set of 4 graphs, multiple choice, and say which one actually could match this equation, I can do that pretty easily just by looking at that. Even if I don't have the old equation, if they just tell me what the leading term looks like, I can tell which one this matches with. So there's your hint why you would want to do this without, a calculator maybe, is you want to know from leading terms and multiplicity, you want to be able to kind of get an idea of what the graph should look like, even if you don't have the whole equation. So there you go. That's it for outcome 6. Just dealing with this leading term test, the multiplicity, using the zeros. We're going to move on from here and actually get back to working with these higher degree equations, but we're going to work into solve them beyond if they're already factored. What if they're not factored for us? That's kind of where we're heading. So we'll see you on the next set.